Hello, I am Mehran Mazanani, and by this tutorial I would like to introduce briefly the new generation of fuzzy inference systems that is called Fractional Fuzzy Inference Systems, FFISs for short. Also, some explanations about the implementation of FFISs in Matlab software are provided. First, let me thank you in advance for choosing this tutorial and your interest in this new generation of fuzzy inference systems. Okay, here we go. Let's take a look at the outline. In this tutorial, we first recall a typical fuzzy inference system. Then conceptual impressions concerning fractional fuzzy inference systems are presented. After that, we see the concept of operating modes. Some illustrative comparisons between FFISs and typical FISs, and the concepts of order and fracture index of FISs. Then we answer some frequent questions regarding the topic. Some of such questions are: what is the relation between FFISs and typical FISs? What's the reasoning mechanism of fractional fuzzy inference systems? What are the differences in the configuration of an FFIs with that of a typical FIS? Why should we apply fractional fuzzy inference systems? I have used type 2 fuzzy inference systems in a problem. There is no way to improve the results. What shall I do? How to apply, how to simulate, how to write the programming code. I have done a project based on Mamdani's FIS, so can I get a better result? How? What shall I do? What are the applications of fractional fuzzy inference systems? Moreover, the last section is devoted to the simulation of FFISs in Matlab software. A point that should be noted is this tutorial in most parts is conceptually and intuitively rather than technically. For technical details, please refer to the following papers. In addition, I have tried to explain the subject in simple words so that everybody can get the points. Before starting the tutorial, let's see the answer to this question. Who should watch this tutorial? Those who would like to get more satisfactory results from FISs. Those who have got a project and would like to improve the results. Those who are looking for new ideas. Those who have worked with fuzzy inference systems and would like to revisit them with more satisfactory results. Those who would like to register some patents. Those who teach fuzzy inference systems and would like to be familiar with a new generation of fuzzy inference systems. Those who are looking for new ways for designing engineering systems. And those who are passionate about learning new ideas in the field of fuzzy systems. Well, as a starting point for our discussion, we should first recall a very brief introduction of fuzzy inference systems and particularly typical fuzzy inference systems. Note that fuzzy inference systems are sometimes called fuzzy control systems or fuzzy logic control, mainly when employed in a control system structure. Before the year 2020, there had been two main fuzzy inference systems: typical fuzzy inference systems and Takagi-Sugeno or TSFIs. The fractional fuzzy inference systems emerged in 2020. A typical fuzzy inference system may be shown in this simple and yet general form in which X is A prime is a minor premise or the input to the system, where A prime is, in a general setting, a fuzzy set. X and Y is R is the major premise that expresses the relation between X and Y by using the fuzzy relation denoted by R. The aim is to infer the fuzzy set B prime as the conclusion or the output of the system. In most applications, the major premise, I mean the relation between X and Y, is expressed by the use of fuzzy if-then rules. In this setting, for the i's rule, A sub I and B sub I are both fuzzy sets. X is A sub I is called the antecedent part, Y is B sub I is called the consequent part. In TS-FIS, the status is a little different. In TS-FIS, the input of the system or the minor premise is mainly a crisp set, and the relation between X and Y in the fuzzy if-then rules are expressed such that the consequent part is a crisp function. In this architecture, the output of the system is also a fuzzy set. Note that if we use the weighted average method, then the output of the TS-FIS is a crisp set. In this tutorial, we don't need anymore to deal with TS fuzzy inference systems. The reason is that fractional fuzzy inference systems are the more general case of typical fuzzy inference systems, and they are both related to fuzzy inference systems in which the consequent part consists of fuzzy sets. In addition, for the sake of simplicity, in most parts, we suppose that there is a single fuzzy if-then rule. So we modify this part. In fractional fuzzy inference systems, the surface structure is completely the same as that of a typical FIS. The difference comes from the deepest structure. In fact, here, a fraction of information resident in the fuzzy relation between X and Y contributes to inferring the fuzzy set B prime sub alpha star. Don't worry about the notations and definitions of B prime sub alpha star or the relation denoted by R sub alpha star. They are defined clearly in this tutorial. The relation between X and Y may also be expressed as a fuzzy if-then rule. Here, the consequent part is a fuzzy set interpreted as the same as the fuzzy set in the consequent part of the typical fuzzy inference system. The difference comes from the way in which the output of the system is inferred, which is explained in this tutorial conceptually and intuitively. Since this tutorial has been devoted to fuzzy inference systems, it is expedient to clarify what we mean by a fuzzy inference system briefly. In a broad sense, a fuzzy inference system is a reasoning system for the explicitation of fuzzy constraints on the variables whose constraints are implicit in a system of fuzzy assignment equations. For example, here, the fuzzy constraint on X is A, and it is explicit, but the fuzzy constraint on Y is implicit in R. Thus, the fuzzy constraint on Y needs to be explicitated. So, the output of FIS is the fuzzy constraint on Y. In fact, FIS explicitates the fuzzy constraint on Y. The other example here, the fuzzy set labeled small is a fuzzy constraint on X, and it is explicit. However, the fuzzy constraint on Y is implicit in the fuzzy relation labeled approximately equal. We need a propagation rule of constraints for the explicitation of the fuzzy constraint on Y. The reasoning mechanism or the propagation rule of constraints is mainly the compositional rule of inference. Most fuzzy inference systems employ such a propagation rule of constraints. However, in fractional fuzzy inference systems, the propagation rule of constraints is called the fractional composition rule of inference. Maybe fuzzy inference systems, in a narrow sense, have been and continue to be the most popular and important approach, which have had a profound impact on recognizing fuzzy set theory as a powerful tool in so many applications. In this sense, fuzzy inference systems are also known as interpolative reasoning. In such fuzzy inference systems, fuzzy if-then rules are employed to describe the relationship between variables x and y, or the dependency of y on x. The output fuzzy set that is a constraint on y is inferred from the application of the composition rule of inference. Well, for more clarification, let us consider a typical fuzzy inference system that includes a single fuzzy if-then rule. F x is A, then y is B. A and B are fuzzy sets, and the input or the minor premise here is x is x0. Hereafter, for the sake of simplicity, we consider inputs as crisp sets. Thus, here, x0 is a crisp set that is a scalar value. By translating the fuzzy if-then rule as a Cartesian product of the fuzzy sets A and B, and also considering the minimum as the base operator in the definition of Cartesian product, the application of the composition rule of inference results in the output fuzzy set. If we define the truest degree of the antecedent part by this relation, then the output fuzzy set can be rewritten in this form. In this setting, the fuzzy inference system is also known as Mamdani's FIS. Thus, the output fuzzy set shown as the green region is inferred from the application of the composition rule of inference on the information resident in fuzzy if-then rule and the given input. If there is a set of fuzzy if-then rules, then the output is obtained by a disjunction of the rules, and if somebody would like to have a crisp output, then they can use a defuzzification method in this regard. Now, we are in the position to start the next section about the conceptual impressions related to the fractional fuzzy inference systems. In our daily life, we almost always make a decision based on the relation between the quality or value and quantity or volume that is implicit or explicit in our goal or the task we are going to do. Such a relation often is made unconsciously in our mind. Some simple examples in this regard are reading a book, magazine, or an article, watching a movie, investing in a project, giving information, driving a car, assessing a person based on his or her CV, buying something, giving a lecture, and so forth. Let's briefly take a look at one of these examples, reading a book. Intuitively, we read a volume of a book or magazine as much as it is informative. In other words, we read a volume of pages of the book as much as our mind values the book. In this case, our mind often unconsciously makes a relation between the value and volume of information included in the book. Such a relation may be considered as a monotone function in our minds. This is also the case for preparing a tutorial. The more time we spend on preparing a tutorial, the more valuable it is. The other cases in this regard are watching a movie, listening to music, paying attention to a lecture, and so forth. As the other example for illustrating the relation between the value and volume of information, let's look at the media's propagation and report of news. We receive many news and information from radio, television, newspapers, and generally from the media in everyday life. The news conveys information. The value of news is related directly to the value of information conveyed by the news. The value of news or information has a major role in determining the volume of news that should be propagated and the amount of time that should be devoted to the report of the news. For example, Suppose that an event happened in a city. The media report the news of this event. If the news is not important, I mean the value of this news is low, then naturally the news is propagated or broadcasted with low volume, and it may be limited to the border of a country or maybe only some neighboring provinces. If the news is important, then the value of information conveyed by the news is high. Thus, the volume of news or information propagated by the media increases. The media may report it in some other countries. If the information included in the news is very important, then the volume of information and news propagated by media becomes very high. So naturally, as it happens in our daily life, there is a relation between the value and volume of information. A question that may arise here is, what would happen if there was no effective relationship between the value and the volume of information? Let us first look at the media example where we suppose that the value of news does not affect effectively the volume of propagation of the information. That is, not effective relation is considered between the value and volume of information in the media. In this status, the media in the world, on all televisions, websites, radios, continuously report news no matter its high or low value. The news that is not important is reported in all the media along with essential news. In the case of reading a book, we suppose that our mind does not effectively relate the value and volume of information. In this status, if we conclude that the book is not informative enough, or in other words, in our opinion, the value of the book is low, so in spite of this fact, we have to read all the pages of the book. However, fortunately, in reality, our mind naturally makes an effective relation between our goals, value, and volume. Such observations help us clearly and briefly express the principal rule in fractional fuzz inference systems. Informally, the principle of the mechanism of inference in FFISs is the exploitation or the maximum exploitation of the information by considering a relation between the value and volume of information. Now, it may be asked that how such a relation is made in fractional fuzz inference systems. As a starting point for our discussion in this regard, we consider a fuzz set as a carrier of information. Such a viewpoint directs us to consider not only the value but also the volume of information included in the fuzz set. Viewed in this perspective, the relation between the value and the volume of the information plays a significant role in making a decision based on given information. In terms of fractional fuzz inference systems, the volume of information is related to an index called the fractional index, here denoted by alpha star, and the value of information is related to the truth degree coming from the antecedent part of a fuzzy-if-then rule. Thus, hereafter, the mu star stands for the value of information, and the alpha star stands for the volume of information. Here, the function f connects the value of information denoted by the mu star to the volume of information denoted by the alpha star. The function f also naturally determines the form of the relation between the value and the volume of information. For example, the linearly simplest relation between the value and volume of information can be expressed in this form. Thus, in this setting, if the value is equal to 1, then the whole volume of information is involved in the process of making a decision. And if the value decreases, then the volume also decreases linearly. Alternatively, if the value increases, then the volume increases linearly. As you have observed, a fraction of information is extracted and a fracture happens in the volume of information from the right-hand side. Such a fracture may also happen from the left-hand side by using the beta fractional index, which also stands for the volume of information included in the fuzzy set. Similar to the previous case, if we consider the linear relation between the value and volume of information, then a fraction of information is extracted for making a decision. And because the beta fractional index has been considered here, a fracture happens in the volume of information from the left-hand side. Well, naturally, some questions might have arisen in your mind. For example, how is the value or quality determined in FFISs? How is the volume or quantity determined in FFISs? What is the difference between these two forms of fractional indices? What is the mechanism of fractional FIS? How can it be applied? How does the volume or quantity emerge in the mathematical relations of FFISs? What's the relation between FFISs and typical FISs? These questions, with so many other questions, will be answered in this tutorial. However, we shall first present some notations and basic concepts in FFISs. As we said, a fuzzy set is viewed as a carrier of information, and from this viewpoint, a relation between the value and volume of information can be made in two forms. One of them may be called the first form or the alpha form, which makes a fracture in the volume of information from the right-hand side, and the other may be called the second form or the beta form, which makes a fracture in the volume of information from the left-hand side. It should be noted that the function that connects the value to the volume in these two forms may be different. In other words, the function in the second form can be different from the function in the first form. For example, it can be a function like g, but it must be a function from the interval 0 and 1 to the interval 0 and 1, or generally a subset of the interval 0 and 1. In so many applications, a fuzzy set is labeled by a word or a concatenation of letters. For example, suppose that a fuzzy set is labeled by positive big. So positive big, or PB for short, is the label of the fuzzy set. In order to distinguish between the first form and the second form, we shall use an arrow on the top of the label of the fuzzy set. For the first form, we consider a right arrow on the top of the label. Such an arrow means that a fraction of the volume of information included in the fuzzy set labeled as positive big is extracted, and the fracture in the volume happens from the right-hand side. For the second form, we consider a left arrow on the top of the label PB. Such an arrow means that a fraction of the volume of information included in the fuzzy set labeled as positive big is extracted, and the fracture in the volume happens from the left-hand side. It should be noted that If the label of a fuzzy set or the name of a membership function is only a letter, then we may use the subscript alpha star or beta star or an arrow on the top of the letter. Otherwise, we may use an arrow to indicate the form. For example, suppose that the name of the membership function of the fuzzy set labeled as positive big is B. Then it is only a letter, so we may use a subscript alpha star to indicate that we have considered the processing of information included in the fuzzy set in the first form. We may also consider a right arrow on this letter. For the second form, if we would like to deal with a letter as a label of the fuzzy set or the name of the membership function, we can also use a subscript or an arrow. They both mean the same. It should be noted that in the literature, sometimes the name of the membership function of a fuzzy set is denoted by mu subscripted by the label of the fuzzy set. The name of the membership function of the fuzzy set positive big here in literature may be shown in this form. However, we ignore such a notation here. Sometimes the label of the fuzzy set is the same as the name of its membership function denoted by a letter. So as we said, we may consider either an arrow on the top of the letter or a subscript to indicate the first and second forms. So when there is only a letter, there are two choices for the notation of the first and second forms. Don't worry about the notations or about the questions that arise in your mind. They will be resolved and answered if we together go on until the end of this tutorial. There are 2 points that should be emphasized here. The first point is about the meaning of notations that have been already defined. I mean the meaning of arrows and subscripts. These notations, in a broad sense, mean that there is a fracture in the volume of information when the information is extracted. And in a narrow sense, they mean that there is a relation between the value and volume of information when it is extracted. As you see here, a fraction of the volume of information is extracted. In most cases, both meanings are the same. The second point is about the definition of a fractional membership function. On the basis of explanations that have been provided so far, such a definition is presented here. Informally, a fractional membership function is referred to as a membership function in which there is a fracture in the volume of information when an inference mechanism extracts the information. At a later point, a more comprehensive definition of fractional membership functions will be presented. As we said, the alpha star and beta star stand for the volume of information, and if they are less than 1, then it means a fraction of volume is used. So there is a fracture in the volume of the extracted information. But here we would like to investigate the case in which the fractional indices are identical to 1. Thus, if the function f is identical to 1, then the fractional index alpha star standing for the volume of information is always equal to 1. Therefore, in notations, we don't need anymore to use the subscript or the arrow, and we write the label of the fuzzy set or the name of its membership function in the usual way. This is also the case for the second form. If the function g is identical to 1, then we have these modifications. There are some important points that should be highlighted here. First, when the label of a fuzzy set or the name of its membership function does not come with any arrow or subscript, it means that the fractional index alpha star or beta star is identical to 1. The second point is that in this case, The information drawn from the fuzzy set in the first form is the same as the information that is extracted from the fuzzy set in the second form. In other words, the first and second forms are the same. For the illustration, see the behavior of the fuzzy set in these two forms, which shows that the same information is extracted from both forms. The other point is that when a fractional index is identical to 1, it can be rewritten in this form because mu star stands for the value of information and its coefficient is 0. Therefore, it can be concluded that in this condition, there is no relation between the value and volume of information. And since the fractional index is identical to 1, so there is also no fracture in the volume of information. As you observe, there is not any relation between the value and volume of extracted information, and also there is no fracture in the volume of information. The last important point is that the extraction of the maximum volume of information happens when the fractional index alpha star or beta star is equal or identical to 1. In other words, based on the previous explanations and notations, when the label of a fuzzy set or the name of its membership function does not come with any arrow or subscript, it means that a full volume of information is extracted from the fuzzy set for any level of the value of information. Now we shall turn our attention to the fuzzy inference systems. The aim is to obtain a conclusion from given inputs and the information located in the fuzzy rule base. The information is processed in the inference engine or the inference block through which the inference fuzzy set, denoted by B sub out, is determined. Here, we would like to revisit the behavior of a typical fuzzy inference system from the viewpoint that has been explained about inferred fuzzy sets. It should be again noted that because we deal with typical fuzzy inference systems, the propagation rule of constraints in the inference block is the compositional rule of inference. For the sake of simplicity, we again consider this case as a typical fuzzy inference system, which is also called Mamdani's fuzzy inference system, and had been presented in the previous slides. We shall mention again that mu star denotes the truth degree coming from the antecedent part. Here, in this case, it is equal to A of x naught. In Mamdani's fuzzy inference system, the output fuzzy set shown by the green region is obtained based on the consequent part membership function clipped or truncated by the truth degree of the antecedent part. The truth degree that comes from the antecedent part, I mean the mu star, determines the value level of the information in the output fuzzy set. So an increase in the truth degree makes an increase in the value of the information resident in the output fuzzy set. As the truth degree decreases, it may be postulated that the value of the output information decreases. By paying attention to different output fuzzy sets that are obtained for different amounts of input, it is easy to see that only the value of the information in the output fuzzy sets changes, but the volume of information does not change. Additionally, based on previous interpretations, the information with maximum volume is extracted from the consequent part. Eventually, we conclude that in typical fuzzy inference systems, a maximum volume of information is extracted for making a decision. There is no relation between the value or quality and volume or quantity of the information in the process of making a conclusion, in the sense we have already explained. The behavior of typical fuzzy inference systems is similar to the status of media in which no relation between the value and volume of information is considered. That is, no matter whether the news conveys the low or high value of information, it should be propagated with the maximum volume. However, for making an intelligent decision, not only the value but also the volume of information should be considered. In a fractional fuzz inference system, the output fuzz set is determined using the fractional composition rule of inference. As is seen, there is an effective relation between the value and volume of information extracted from the consequent part. The next sections will discuss the mechanism, notations, and fuzz-if-then rules in fractional fuzz inference systems. Let's look at another illustrative example that shows the difference between reasoning mechanisms in typical fuzz inference systems and fractional fuzz inference systems. This is a case that may happen in our life. Here, the lady may change the channel and stop watching the movie, but the man disagrees and says, "Let's watch it through." He gives this reason that the movie is not bad. However, the lady reasons that we should watch the movie as long as it is worthy of enough. In fact, she means that the volume of the movie watched should be dependent on the value of the movie. Thus, in other words, here, the reasoning mechanism that the lady uses is similar to the reasoning mechanism that is used in fractional fuzz inference systems. But the man uses the reasoning mechanism that is applied in typical fuzz inference systems. This time, as you see, the remote control is with the man. He's watching a movie and he's going to watch it through because he reasoned that the movie does not lack the value. The man reasons like the mechanism in typical fuzz inference systems, but the lady does not watch the movie anymore. She has realized that they should relate the value and volume of what is watched. A question that may arise here is that, where does such a difference between reasoning mechanisms come from? A simple answer to the question is, typical fuzz inference systems often employ the composition rule of inference. The composition rule of inference always extracts the maximum volume of information, whatever its value, for concluding. There is no practical relation between the value and volume of information in the composition rule of inference. In other words, the composition rule of inference, acting as the propagation rule of constraints, propagates the maximum volume of information from premises to the conclusion. However, fractional fuzz inference systems employ the fractional composition rule of inference. The fractional composition rule of inference exploits the relation between the value and volume of information for concluding. In the fractional compositional rule of inference, extracting the maximum volume of information is not always necessary. In other words, the fractional composition rule of inference, acting as the propagation rule of constraints, is able to propagate a fraction of the volume of information from premises to the conclusion. Well, based on our discussion till now, a comparison between fractional FISs and typical FISs can be drawn here in this table. As is seen, the exploitation of information in fractional FIS is based on the value and volume. However, in typical FISs, it is only based on the value, in the sense that we have explained so far. In fractional FISs, there is no necessity for extracting the maximum volume of information, but it is a necessity in typical FIS. And also, if somebody asks us about the existence of a relation between the value and volume of extracted information, then the answer for the fractional FISs is yes, and the answer for typical FISs is no. Here, again, I would like to emphasize on this point that you might have got some questions about fractional FISs, or you may be a little confused. Indeed, it is natural, but I suggest you write down your questions and go on. Highly likely, this tutorial will provide some answers to your questions if you watch it through. Now, we continue our discussion on fractional fuzzy inference systems by introducing the concept of operating modes. To present the concept of operating modes in FFISs, we shall first explain the notations of fuzzy if-then rules in fractional fuzzy inference systems. The fuzzy if-then rules often are written based on the fuzzy sets considered for the inputs and outputs. Assume that there is one input and one output. Each of them consists of only one fuzzy set, as shown below. The fuzzy set of the antecedent part has been labeled as negative big, or NB for short, and the fuzzy set of the consequent part has been labeled as positive big, PB. So the fuzzy if-then rule is written as fx is NB, then y is PB. As we said, in FFISs, a relation between the value and volume of information resident in focal fuzzy sets is considered. The focal fuzzy sets in FFISs are only the fuzzy sets in the consequent part fuzzy sets plane. In other words, only the fuzzy sets in the consequent part fuzzy sets plane, for example, PB in our case, are those in which a relation between the value and volume of information is made. This means that a fracture of the volume of information happens only in the fuzzy sets of the consequent part. As was already expressed and shown in the previous slides, such a fracture, or the relation between the value and volume of information, can be considered in two ways. In the first form, or alpha form, and in the second form, or beta form. If we consider the membership function of the fuzzy set positive big as fractional membership function in the first form, then we should put a right arrow on the top of the label of the fuzzy set PB in the fuzzy if-then rule. Therefore, the alpha star index may also come with the subscript PB, indicating that this fractional index corresponds to the fuzzy set labeled PB, or positive big. As was stated before, the fractional index alpha star in a general setting can be a function of mu star, and mu star is a truth degree coming from the antecedent part. The domain of the function f is the interval 0 and 1, and the range of the function is also the interval 0 and 1, or a subset of the interval 0 and 1. Hence, the alpha star can also be a constant drawn from the interval 0 and 1. Some examples have been shown here. But if the membership function of the fuzzy set PB in the consequent part fuzzy sets plane is a fractional membership function in the second form, then a left arrow on the top of its label should be considered in the fuzzy if-then rule. Similar to the first form, here we may put a subscript PB for the fractional index beta star to indicate that it corresponds to the fuzzy set labeled PB. The fractional index beta star in a general setting can also be a function of the mu star. Some examples in this regard have been shown here. Eventually, we only need to add an arrow on the top of the label of a fuzzy set in the consequent part of the fuzzy if-then rule to express the fact that a fracture of the volume of information is extracted from the fuzzy set PB. Indeed, in this way, we also say that such a fracture happens from right or left. A point that we always should keep in our mind is that when we are talking about a fuzzy inference system, while we only show or write fuzzy if-then rules, we always implicitly assume that there is an appropriate number of inputs coming along with the fuzzy if-then rules. And there is a propagation rule of constraints for inferring the output fuzzy set. But to have a tidy screen, we don't need to write the inputs to the system, and always keep in mind that the aim is to infer the output fuzzy set by a propagation rule of constraints. So for example, in this case, you see now on the screen, by the fuzzy inference system we mean this form, where there is a minor premise, I mean the input x is x naught, and the aim is to infer the fuzzy constraint on the output by a propagation rule of constraint. But we have ignored to write this form for the simplicity, and we only write the fuzzy if-then rule. A question may arise here. Although we have already answered it, it is expedient to highlight it. The question is, what is the meaning of the following fuzzy if-then rule? Fx is negative big, then y is positive big. Or is its meaning different from that of the conventional fuzzy if-then rule? The answer is, the meaning of the above fuzzy if-then rule is the same as that of the conventional fuzzy if-then rule. Both of them mean that if the input x is negative big, then the output y is positive big. But writing the fuzzy if-then rule in this way also gives us some information about the deep structure of the processing of information. Specifically, in the above case, it expresses that there is a fracture in the volume of information extracted from the fuzzy set labeled positive big, and such a fracture is in the second form or beta form. In other words, it says that extracting information from the consequent part is not necessarily on the basis of the maximum volume of information resident in PB. In other sense, if there is an arrow on the top of a fuzzy set in the consequent part, then it means that the propagation rule of constraints is a fractional composition rule of inference. Let's again recall this fractional fuzzy inference system, which consists of only one single fuzzy if-then rule, and there is only one single fuzzy set in the consequent part fuzzy set's plane. By considering the membership function of the fuzzy set PB as a fractional membership function in the first or second form, we arrive at an operating mode of fractional fuzzy inference system. For example, here the membership function of the fuzzy set PB has been considered as a fractional membership function in the second form. So we say that this fuzzy inference system is an operating mode of fractional fuzzy inference system. Is there another operating mode? Yes, there is. As you might have guessed, the other operating mode is when we consider the membership function of the fuzzy set PB as a fractional membership function in the first form. From this observation, it is easy to state that if the consequent part fuzzy set's plane consists of only one single fuzzy set, there are two operating modes of FFISs. The concept of operating modes of FFISs means that there are some FFISs that are different in deep structure but the same in the surface structure, and they all correspond to the same typical fuzzy inference system. The number of operating modes may be viewed as the number of ways in which a typical fuzzy inference system can be converted to its corresponding fractional fuzzy inference system. For example, here in our case, there are two ways for converting a typical fuzzy inference system to its corresponding fractional fuzzy inference system. One of them is made by the second form and the other by the first form. Those willing to go through the technical details are advised to look at the original paper for more clarification about the meaning of corresponding in the stated sentences. Somebody may ask us about the case where there is more than one fuzzy set in the consequent part plane. Well, here we go. First, let's suppose that there are two fuzzy sets in the consequent part fuzzy sets plane. As you see on the right hand side, there are two fuzzy sets labeled as positive big, PB for short, and positive small, PS. Since the membership function of each of them can be considered as a fractional membership function in the first or second form, there are four FFISs in different operating modes. Then let's figure them out. There are two fuzzy sets in the antecedent part plane and two fuzzy sets in the consequent part plane. And then there are two fuzzy if-then rules, which makes a fuzzy relation between the variables x and y. Suppose that the fuzzy rules are fx is nb, then y is pb. Fx is negative small, then y is positive small. Thus, this is a set of two fuzzy if-then rules used in a typical fuzzy inference system. We know that these fuzzy if-then rules, along with an input and the composition rule of inference, constitute a typical fuzzy inference system. Let's start to figure out the first mode. Suppose that the membership functions of both fuzzy sets PB and PS in the consequent part plane are fractional membership functions in the first form. Then we can write fuzzy if-then rules of an FFIS as you see here. And now we could constitute one of the four modes. So in the first mode, we have considered the fractional membership functions of PB and PS in the alpha form. This time, let the fractional membership function of PB be in the first form. But we change the fractional membership function of PS to the second form. In this setting, we can write the fuzzy if-then rules of FFIS using the corresponding arrows and arrive at the second mode of FFIS. To create the third mode, we can change the forms of both fractional membership functions for PB to the second form and for PS to the first form. The fourth mode can also be constituted similarly. As was stated already, these modes mean that corresponding to the typical fuzzy inference system, there are four fractional fuzzy inference systems in different operating modes, each of which may be used and chosen for our purposes. So if the consequent part fuzzy sets plane includes only one fuzzy set, then there are two FFISs in different operating modes. If there are two fuzzy sets in the consequent part plane, then there are four operating modes. So what do you guess if there are 5 fuzzy sets in the consequent part plane? You might have correctly guessed that there are 2 to the power of 5 FFISs in different operating modes. Eventually, it turns out that there are possibly 2 to the power of m operating modes of FFISs corresponding to a typical FIS, where the consequent part fuzzy sets plane consists of m fuzzy sets. Thus, the degrees of freedom in the design of fuzzy systems and the applications of FFIs increase significantly. Note that in each operating mode, an FFIs can also take an order from 0 to 1. The concept of order of fuzzy inference systems will be presented in this tutorial. These are the unique features coming with fractional fuzzy inference systems and result in expanding the space of solutions or outputs more than before. In other words, fractional fuzzy inference systems open a gate to a space of fuzzy systems output that used to be indiscoverable. Thus, now we can obtain solutions that typical fuzzy inference systems couldn't obtain. A natural question that may arise here is, which mode should be chosen? The answer to this question can be found when some suggestions for the design of fractional fuzzy inference systems are given and some modes of FFISs are defined. We would like to investigate some essential remarks from this page until the end of this section. So, the first remark. Consider this single fuzzy if-then rule, which is related to a fuzzy inference system. As you see, there is no arrow on the top of the fuzzy set PB, which is equivalent to say that the fractional index in the fractional membership function of PB is equal to 1. Equivalently, as you may remember, we can say that the maximum volume of information is extracted. Since the maximum volume of information extraction happens in typical fuzzy inference system, this part is also equivalent to saying that we deal with typical fuzzy inference systems. And we know that in typical fuzzy inference systems, a fuzzy if-then rule is written in this form. Well, since there is no arrow on the top of the fuzzy set of the consequent part, we can say that the fractional index in the fractional membership function of PB is equal to unity, and no fracture in the volume of information happens. Thus, the maximum volume of information is extracted from PB. In other words, the above fuzzy if-then rule works in the setting of typical fuzzy inference systems. Consequently, the following expressions are equivalent. There is no arrow on the top of the fuzzy set of the consequent part. The fractional index is equal to unity in the fractional membership function of the fuzzy set. There is no fracture in the volume of information. The maximum volume of information is extracted from the fuzzy set. The fuzzy if-then rule works in the setting of typical fuzzy inference systems. Second remark. As we said, in fractional fuzzy inference systems, only the membership functions of the fuzzy sets in the consequent part plane are considered as fractional membership functions. Now, suppose that what you see on the screen is the consequent part fuzzy sets plane. So if we consider a fractional membership function for the fuzzy set labeled NB in the first form, then its fractional index in a general setting can be a function of mu star, and by mu star we mean the truth degree coming from the antecedent part. The fractional index can also be a constant drawn from the interval 0 and 1. But if it is a function of mu star, then the function ranges over the interval 0 and 1, or a subset of the interval 0 and 1. This remark is intended to highlight that if we consider a fractional membership function for the fuzzy set labeled NS in the first form, then its fractional index can be a constant or a function of mu star, but different from the fractional index of NB. Thus, if the fractional membership functions of two fuzzy sets are in the same form, it doesn't mean that their fractional indices are the same. This is also the case for the second form. For example, as you see, the fractional membership functions of fuzzy sets labeled by Z, PS, and PB are all in the second form, but each of them has its own fractional index, which can be different from others. In other words, some of them can be constant with different values, and the others can be different functions of mu star. So in this case, the FFIs can be made by 5 different constant or functional fractional indices. The third remark is intended to highlight a point that comes from a combination of the first and second remark. As we said, a fractional index can be a constant or functional. Some examples are shown here. Now, here we would like to highlight the case where the fractional index is identical to 1 and answer two questions. What does happen if the fractional index is equal or identical to 1? And what does it mean? Suppose that the fractional index of the fuzzy set NB is identical to 1. From the first remark, the equivalent expressions, we know that when the fractional index is identical to 1, equivalently, we can say that the maximum volume of information is extracted from the fuzzy set NB. Also, equivalently, it means that we deal with a fuzzy if-then rule in the setting of a typical fuzzy inference system, for which we don't consider any arrow on the top of the label of the fuzzy set. So, when the fractional index of NB is identical to 1, it means that extracting information from NB with the right arrow is the same as the NB without any arrow. I mean, in this condition, there is no fracture in the membership function of NB with the right arrow. Eventually, we omit the arrow from the top of NB. In this setting, the fuzzy if-then rule, whose consequent part includes the fuzzy set NB, works the same as the fuzzy if-then rule of a typical fuzzy inference system. For more clarification in this regard, first let's a little clear and tidy the screen. Okay. So here we have a fractional fuzzy inference system whose consequent part, fuzzy sets plane, have been shown on the right hand side, which also indicates the operating mode of FFIS. The antecedent part, fuzzy sets plane, can be seen on the left hand side. For this FFIS, let's suppose that there are 5 fuzzy if-then rules, and also assume that the input is in this position. So in this condition, only the first and second rules are active. Thus, let's focus only on these rules. Associated with them are these fractional indices. We know that corresponding to this FFIS, there is a typical FIS that is shown here. We also know that in the FFIS, the propagation rule of constraints is the fractional composition rule of inference. That is why we have considered the arrows on the top of the labels of fuzzy sets, which of course equivalently means that the membership functions of the fuzzy sets are of the type of fractional membership functions. In typical FIS, the propagation rule of constraints is the composition rule of inference. Therefore, except the propagation rule of constraints, everything is the same in these two fuzzy inference systems. It is easy to state that as long as the fractional index associated with the fuzzy set NB is not equal to 1, the output of R sub 1, the first rule in FFIS, is different from the output of R star sub 1, the first rule in typical FIS. The reason is that when the fractional index alpha star sub NB is not equal to 1, then there is a fracture in the volume of information extracted from the first rule in FFIS. However, in the typical FIS, a maximum volume of information is extracted from the first rule. In other words, there is no fracture in the volume of extracted information. We also have the same case for the second rule in both FISs. I mean, here also the output of the second rule in both FISs are different as long as the fractional index alpha star sub ns is not equal to 1. Now we discuss the condition where the outputs of fuzzy if-then rules are the same. Let's consider the first rules in these two FISs. The outputs of R sub 1 and R star sub 1 are the same as long as the fractional index alpha star sub NB is equal to 1. So under this condition, these two fuzzy if-then rules produce the same output. We have explained the reasons in this regard in the previous slides, but briefly speaking, when the fractional index is equal to 1, there is no fracture in the volume of information inferred from the fuzzy if-then rule. In other words, a full volume of information is derived from the fuzzy if-then rule. A question that arises here is, when does such a condition hold? There are two cases. First, when the fractional index is identical to 1, or equivalently, it is a constant and equal to 1. In this case, since the output of the first rule in the FFIS is always the same as the output of the first rule in the typical FIS. So according to the first remark, we shall omit the arrow from the top of the label of fuzzy set NB. The second case is when the fractional index is a function of mu star, and in some situations it is equal to 1. In this case, the outputs of two rules R sub 1 and R star sub 1 are the same only for the situations where the mu star values satisfy this equation. The roots of this equation are called touch points. In fact, touch points are the points at which the fractional FIS touches the typical FIS. The touch points are determined by solving this equation. At touch points, the information is extracted with maximum volume from the fuzzy set. Let's look at an example for finding the touch points. Assume that this is the functional fractional index for MB. Then by equating it with the value 1 and solving the equation, we get to this result that if the input denoted by x0 is in a position that the truth degree of the first rule is equal to 1, then the first rules in FFIS and typical FIS have the same outputs. For more illustration, look at the input on the left-hand side, which shows some of the situations where the FFIS meets its touch points. For example, if the input is in this position or here or this position, then the outputs of the two rules are the same. It should be noted that because the rules are not always the same, but only for some situations, we keep the arrow on the top of the label of the fuzzy set NB in the FFIS. Let's look at the other example. Suppose that the functional fractional index for MB is a sine function in this form. Similar to the previous example for finding the touch points, we should consider this equation, whose solution can be found based on this relation that is modified to this one. And by some simplifications, we have now the touch points come out by assigning different integer values to k. For k equal to 0, we have two values, but one of them is negative, which is not acceptable because the truth degree must be a number in the interval 0 and 1. For k equal to 1, 2, and 3, we have got these touch points. And for k equal to 4, the value of mu star becomes more than 1. That is not acceptable. Eventually, for this case, we have got 8 touch points. In comparison with the previous example, that we have got only one touch point, here having 8 touch points means that if we consider the functional fractional index as the sine function, the number of positions in which the outputs of FFIS are the same as the output of typical FIS increases. Specifically, the more touch points, the more fractional FIS touches the typical FIS. I should say that touch points have not been presented in the original paper, and here it is the first time they are introduced. Touch points will be introduced with more details in one of our upcoming papers. Touch points make us able to design, analyze, and customize fractional FISs for our purposes, the capability that can't be found in typical FISs. We shall not go through the details of touch points anymore. Let's again consider our FFIs in this mode. In most applications, there is a fuzzy set labeled as 0 or Z for short. in the center of the consequent part fuzzy set's plane. Since this fuzzy set is symmetric with respect to the vertical axis standing for the membership degree, the fractional index associated with this fuzzy set should be identical to 1. Such a setting results in outputs that are not biased when only the fuzzy if-then rule related to the fuzzy set Z is active. This setting is applicable particularly in control system structures. Under this setting, we have got a mode of FFISs in which all the fractional membership functions of the fuzzy sets in the right-hand side of the consequent part plane are in the second form, and all the fractional membership functions in the left-hand side of the plane are in the first form. This mode is called the aggressive mode. The aggressive mode is suggested to be considered as the mode of FFIs, mainly in control system structures. The other mode that should be highlighted is the anti-aggressive mode. If in the aggressive mode, the first forms are replaced by the second forms, and reciprocally, the second forms by the first forms, then we have got the anti-aggressive mode. The last remark of this section is about this question. What if we set all the fractional indices of a fractional FIS to unity? So let's see what happens. Based on the explanations provided so far and the previous remarks, we know that when the fractional index is identical to 1, we omit the arrow from the top of the labels of fuzzy sets. So what have we got? You might have guessed that. Yes, by this setting, we have arrived at a typical FIS from the FFIs. Thus, if all the fractional indices of fuzzy sets in a fractional fuzzy inference system are identical to unity, then the fractional FIS reduces to its corresponding typical FIS. In other words, now we know one of the relation between fractional FISs and typical FISs, which says that typical FISs are a special case of fractional FISs. The results of this section add this row to the comparison table. The fractional FISs are multi-modes fuzzy inference systems. However, typical FISs are single mode. Now it's time to look at some illustrative examples to understand better the points explained so far. But before starting this section, let's have a break time and then continue the tutorial. As we said in this section, some more illustrative comparisons between fractional FISs and typical FISs are shown. But it is expedient to summarize the points expressed so far. We have viewed a fuzzy set as a carrier of information. Information can be considered by the value and volume. There are two forms based on which the membership function of a fuzzy set can be regarded such that a relation can be made between the value and volume of information resident in the fuzzy set. These two forms are called the first form or alpha form and the second form or beta form. The membership function that is made based on each form is called the fractional membership function. And indeed, in another sense, a fractional membership function is defined as a membership function from which a fracture of the volume of information is extracted. Later, we give a more comprehensive definition of a fractional membership function. So let's go on to the other points. In these two forms, the alpha star and beta star are called fractional indices, and they stand for the volume of information. Mu star stands for the value, and it is the truth degree that comes from the antecedent part, the firing level of the rule. For example, if we have an input in this position, then two rules are fired, and two truth degrees stand for the value of information in the consequent part. These truth degrees are used to determine the values of the fractional indices in the fired rules and the volume of information that should be drawn from the fuzzy sets in the consequent part of these two rules. The relation between the value and volume of information is determined by the use of a function in each form. If a fractional index is not a constant but a function of mu star, then we may also call it functional fractional index. About the meaning of notations, a right arrow is put on the top of the label of the fuzzy set for the first form and a left arrow for the second form. Meanwhile, if the label of a fuzzy set is only a letter, or if we want to use the name of the membership function, then we can use an arrow or a subscript for the notations. We have discussed the concept of modes of FFISs and explained that the concept of modes of FFISs means that there are some FFISs that are different in deep structure but same in the surface structure, and they are all corresponding to the same typical fuzzy inference system. A mode in FFIs is determined based on a set of forms of fraction membership functions in the consequent part plane. For example, what you see on this screen shows a mode of FFIs. If we change the form of fractional membership function of PB from the second form to the first form, then now we have got an FFIs in a different mode. Another mode can also be achieved if we change the form of fractional membership function of NS to second form. Eventually, it turns out that for a fuzzy inference system with a consequent part plane consisting of M fuzzy set, there are possibly 2 to the power of M modes of FFIs. We have also, for the first time, here introduced the concept of touch points, the concept that can't be found in typical FISs. By definition, touch points are the points at which the fractional FIS touches the typical FIS. The roots of this equation determine the touch points. At touch points, the information is extracted with maximum volume from the fuzzy set. Additionally, at touch points, the rule in which the consequent part consists of this fuzzy set is the same as the rule in the typical FIS. We don't omit arrows in this case. If the fractional index of a fuzzy set is identical to unity, then the information is extracted with maximum volume from the fuzzy set. Additionally, the rule in which the consequent part consists of this fuzzy set is the same as the rule in the typical FIS. We also consider no arrow on the top of the label of this fuzzy set. And when all the fractional indices are identical to 1 or unity, then the fractional FIS is reduced to its corresponding typical FIS. So here we go. For comparison, we consider a single input, single output fuzzy system consisting of only one fuzzy if-then rule, where the fuzzy set labeled as A is a triangular fuzzy number whose core is 1. The fuzzy set labeled as B is also a triangular fuzzy number whose core is 6. The fuzzifier is a singleton. The defuzzifier is a centroid. The propagation rule of constraints in the inference block is the composition rule of inference, and the base operator is the minimum. Thus, this is a typical fuzzy inference system that you are familiar with by the name of Mamdani's FIS. The input is a crisp input that varies from 0 to 2. And we aim to compare the output fuzzy set and the defuzzified output of the system with its corresponding fractional fuzzy inference system. This is the configuration of the fractional fuzzy inference system. As you see, everything is the same as the previous typical fuzzy inference system. Still, the difference comes from the inference block, where the propagation rule of constraints in the FFIs is a fractional composition rule of inference. Since the fractional composition rule of inference needs to know how to make a relation between the value and volume of information extracted from the fuzzy set labeled B in the consequent part, so we should determine the form of such a relation. Here, the consequent part fuzzy set's plane includes only one single fuzzy set B, so there are two modes. We start with the first form, and then in the simulations we will show the outputs for the second form. Similarly, the crisp input varies from 0 to 2 to obtain the fuzzy set and the fuzzified outputs. It should be noted that all the simulations concerning fractional fuzzy inference systems have been done based on the Matlab M file FFIS.m. We have also considered various functions that will be assigned to the functional fractional index to observe different behavior of FFIS compared to its corresponding typical FIS. As you see, all these functional fractional indices range over 0 and 1, and they can be linear, nonlinear, wavy, polynomial, and so forth. In the upcoming simulations, an important point will be explained, which reveals one of the most important differences between the fractional fuzzy inference systems and typical fuzzy inference systems. Well, let's start. Here, the green region shows the output fuzzy set. The functional fractional index is the simplest linear function of the truth degree. In other words, there is a linear relation between the value and volume of information drawn from the fuzzy set B. As you see, in the fractional FIS, the volume of information linearly varies by the variation of the value. However, in typical FIS, the maximum volume of information is always used to infer the output fuzzy set, and it does not vary. This time, the functional fractional index is a sign function for which we had obtained the touch points. In the following slides, we show you the touch points, but this result helps you have an impression of the wavy behavior of the FFIs when the fractional index is a sign function. Here, the diffusification of the output fuzzy set has also been shown. The blue curve shows the output of FFIs, and the red curve shows the output of the typical FIS. There are some points that need to be explained in this simulation. One of them is about the touch points. As you see here, the fractional index is a linear function of the mu star. The roots of this equation give the touch points. This equation has got only one single root when the mu star is equal to 1. So whenever the mu star is equal to 1, the FFIS touches the typical FIS. Here, the other functional fractional index has been assigned to the fuzzy set B. In this setting, as you see, there is only one touch point that can be also verified by solving this equation. Now, we would like to see the behavior of FFIs when the functional fractional index is a signed function for which we had obtained 8 touch points. So here we go. As you see and verify by solving this equation, there are 8 touch points that can be observed here. It should be realized that since the values of truth degrees are repeated while the input x is larger than 1, then the touch points are also repeated. For more clarification, let's count the number of touch points while the input x is less than 1. 1, 2, 3, 4, 5, 6, 7, and 8, while the input x is less than 1, as we expected. Now, let's see the output of FFIs in the other mode related to the second form or beta form of fractional membership function of the fuzzy set B. The second form is a linear function in the first examination, a linear relationship between quality and quantity. As we expect, there is only one touch point, and also the output of this mode is different from the other mode. To distinguish between these two modes, let me again show both of them in the same framework. There is only one touch point in both modes, and their touch point is the same. That's why they meet each other in the same place. Additionally, this slide shows that when the fractional membership function is in the second form, the crisp output of the fuzzy system is algebraically larger than the typical fuzzy system and the fuzzy system in the first form. Meanwhile, when the fractional membership function is in the first form, the crisp output of the fuzzy system is algebraically the smallest. Thus, the difference between the effect of considering first form and second form fractional membership functions in the output of fuzzy inference systems can be shown here, which says that the defuzzified output of fractional fuzzy inference systems with more fractional membership functions in the second form is algebraically larger than the typical fuzzy inference system, and the fractional fuzzy inference system with more fractional membership functions in the first one. In addition, the defuzzified output of fractional fuzzy inference systems with more fractional membership functions in the first form is algebraically the smallest. This is another example in which the second form has been considered for the fractional membership function of B, and the fractional index is a combination of sine and exponential functions. By looking at the outputs, now you might have guessed that there is only one touch point. Of course, yes, you can also solve that equation related to touch points and find out that the equation has only one single root. This is the other example in which the second form has been considered for the fractional membership function of B, and the fractional index is the absolute value of a polynomial. As you see, there are two touch points, which means that if you solve that equation related to touch points, then you find out that the equation has two roots. You may be wondering that why such a volume of simulations has been shown. What's the other point that may come from those? First, Let us again look at the outputs of fuzzy systems that have already been obtained. As you see, we have got a wide variety of results by using FFIs, the blue curves. Only one single result from the typical FIS, the red curve. We would also obtain a lot of different results based on two modes of FFIs and other functional fractional indices. One of the points that should be noted is all of these different results have been obtained based on the same fuzzy inference system configuration. In other words, to get these results, the fuzzifier has not been changed. The defuzzifier has not been changed. The general structure of fuzzy sets has not been changed. The inputs have not been changed. And the fuzzy if-then rule has not been changed. All these constituents of fuzzy systems have been the same between the typical FIS and the fractional FIS. Only the inference mechanism of the two FISs has been different. FFIS, on the basis of its inference mechanism, can make a relation between the value and volume of information extracted from the fuzzy set in the consequent part. Such an ability has been inspired from the ways in which humans make a relation between the value and volume of imprecise information for their rational decisions. This ability enables FFIs to extend the space of fuzzy system output. This extension results in discovering solutions or outputs that used to be indiscoverable by typical FIS. One of the most important results of this discussion and the observations you have had so far is that FFIS enables us to obtain the solutions or outputs from fuzzy systems that we couldn't obtain by using typical FISs. This means that now we can increase the accuracy of the model. One of the major issues in first-order or typical fuzzy inference systems is to make a trade-off between accuracy and interpretability. In fact, obtaining high degrees of interpretability and accuracy is a contradictory purpose. Specifically, in most cases, if you increase the accuracy, then the interpretability is sacrificed. Reciprocally, if you increase the interpretability, then the accuracy is sacrificed. But fractional FISs overcome such an issue significantly. As you have observed in the examples, by applying FFISs without making any significant change in the fuzzy system configuration, the accuracy can be increased by the use of the capability of FFIs in producing a lot of different outputs without affecting the interpretability. Therefore, abstractly, the question is answered in two parts. First, by the use of FFISs, the space of fuzzy system outputs is extended and enlarged such that the space of typical FISs outputs may be viewed as a point in the space of FFISs outputs. Someone may ask this question: why is the space of FFISs outputs larger than that of typical FISs outputs? Although we have already provided some explanations in this regard, an abstract answer is that FFISs are fuzzy inference systems from fractional order, such that the order ranges over the interval 0 and 1. However, typical FISs are fuzzy inference systems from first order, which means that the order is a single point in the interval 0 and 1, that is equal to 1. The second part of the answer is, in FFISs, the interpretability is retained while the accuracy increases. These two statements are related to each other. To have a more precise impression of the extension of the fuzzy system outputs through the application of FFISs, let's look at a fuzzy system consisting of two rules. So here, the fuzzy inference system is in the same configuration as the previous one. The only change is that there are two fuzzy sets in the consequent part plane and two fuzzy if-then rules here. It should be realized that because there are two fuzzy sets in the consequent part plane, then there are four operating modes for the FFIs. Based on the arrows on the top of the labels of fuzzy sets, it can be easily recognized in which mode the FFIs works. We first start by the mode in which both the fractional membership functions of B sub 1 and B sub 2 are in the first form. Similar to the previous simulations, the input varies from 0 to 3. Here, both the functional fractional indices are linear functions. As is seen, the infinite fuzzy sets shown by the green region in FFIs are always a fraction of those inferred by the typical FIs, except in the touch points. In the touch points, both the green regions and so the differenzified outputs are the same. As we said, in this FFIs, there are two fuzzy sets in the consequent part plane, and thus there are four different operating modes. Now, let's look at the behavior of FFIs in four different operating modes in the same framework. Okay, here we go. You observe that while FFIs and typical FIs have got the same configuration, by the use of operating modes of FFIs, we can discover different outputs. This is why we have not made any change in the input, output, fuzzy rules, fuzzifier, or defuzzifier, except the inference mechanism. This observation also shows that typical FIS always works in the single mode, but FFIs can work in multi-modes. I would like to highlight that all the functional fractional indices are linear functions of the same type in these simulations. So if we consider different functions, then naturally we obtain different outputs. Now, it could have been imagined how much the space of fuzzy system outputs has been enlarged. But to demonstrate this fact, let's have some more examples. This time, the fractional indices are nonlinear functions, different from each other. Due to the presence of sine function, there are a considerable number of touch points. In this example, one of the functional fractional indices is a sine function and the other is a cosine. Therefore, according to already aforementioned, it is clear that the number of times that FFIs touches the typical FIS is more than the number of touches in previous examples. There are two more examples by which this section is closed. In this example, the fractional indices are polynomial. The functional fractional index of B sub 2 is a linear function. When the input is larger than or equal to 2, then only the fuzzy if-then rule associated with the fuzzy set B sub 2 is active. Then we expect that there is only one single touch point when the input is larger than or equal to 2, which is indeed verified as you observe. Now let's investigate a case similar to the previous one, but this time the functional fractional index of B sub 2 is identical to 1. Before starting the simulation, let's share our opinion. Based on the explanations provided in the previous sections, We expect that the output of the second fuzzy if-then rule in FFIs that includes the fuzzy set B sub 2 is completely the same as the output of the second fuzzy if-then rule in the typical FIs. In addition, when the input is larger than or equal to 2, only the second fuzzy if-then rules in FFIs and typical FIs are active. Thus, we expect the outputs of FFIs and typical FIs are the same when the input is larger than or equal to 2. Now, let's take a look at the outputs. Okay, here we go. So, what we expected happened, and the outputs of two fuzzy inference systems are the same when the input is larger than or equal to 2. The last point in this section is about the functional fractional index. Generally, a fractional index can be considered as a function ranging over the interval 0 and 1. Such a fractional index is called the functional fractional index. A functional fractional index reflects a direct connection between the value and volume of the information. Specifically, if the function is a monotonically increasing function, then we can state that the more valuable the information, the more significant the volume of the information involved in making a conclusion. In our daily life, we often make a decision based on the above statement. That is, our mind often creates a relation between the quality and quantity in the first form, or alpha form, by the use of a monotonically increasing function. This fact directs us to state that basically fractional fuzzy inference systems derive their inspiration from the informal ways in which humans make a relation between the value and volume of imprecise information for their rational decisions. Eventually, on the basis of the discussions expressed in this section, we can add this row to the table. In the next slides, we investigate the concept of the order of fractional fuzzy inference systems. One of the results of this concept is that we realize that typical fuzzy inference systems are first-order fuzzy inference systems. The concept of fracture index. One of the results of this concept is we realize that the fracture index of typical fuzzy inference systems is 0. In other words, there is no fracture in typical fuzzy inference systems. The necessity of FFISs. One of the results of this discussion is that you might ignore the use of typical type 1 and type 2 fuzzy systems. Answering some questions. One of the results of this section is that you might find some answers to your questions. The implementation of fractional fuzzy inference systems in Matlab environment by the use of the M-file function FFIS.m. One of the results of this section is that you will be able to implement and simulate your own project by the use of fractional fuzzy inference systems in Matlab software. In this section, the concepts of order and fracture index of fuzzy inference systems are explained. These concepts are used for ranking, comparing, and designing fuzzy inference systems. Uniquely new concepts coming from fractional fuzzy inference systems. But before starting the next section, let's have a break time. Let's start the fourth section that is about uniquely new concepts of order and fracture index of fuzzy inference systems. Well, Here we go. Someone may ask us this question: why do you call this type of fuzzy inference system the fractional fuzzy inference system? In fact, there are some reasons, some of which have already been observed by illustrations and explanations. The fact is, FFISs are fuzzy inference systems from fractional order, and typical FISs are fuzzy inference systems from first order. The concept of order for fuzzy inference systems is a uniquely new concept introduced for the first time in 2020 in the original paper in which the fractional fuzzy inference systems have been introduced. Along with this fact, briefly answer to the question is because such a fuzzy inference system is from fractional order. The fracture index of such a fuzzy inference system is not zero. That is, there is a fracture in the inferred fuzzy set. A fraction of the volume of information resident in fuzzy sets is exploited. The inferred fuzzy set in FFIS is a fraction of the inferred fuzzy set in typical FISs. The order of an FFIS is defined based on the left and right orders. So first, these orders are defined. The left and right orders of a fractional fuzzy inference system are defined respectively by these relations, where P and Q are respectively the number of consequent part fractional membership functions that are in the form of alpha and beta. I mean the first form and second form. The alpha star sub I and beta star sub j are the values of fractional indices, and n is the number of consequent part membership functions, or the number of fuzzy sets in the consequent part plane. Some illustrative examples are presented such that these relations will become clear. The order of a fractional fuzzy inference system is defined by the pair R and S, where R and S are the left and right orders of the fractional FIS. Let's have some examples. Suppose that there is an FFIS in this mode. The table shows the values of the fractional indices. For example, look at the fuzzy set labeled by PB. It is in the second form or beta form, and its corresponding fractional index is beta star sub PB, that is equal to 0.5. The definitions of left order and right order have also been duplicated here. In these relations, n is the number of membership functions or fuzzy sets in the consequent part fuzzy sets plane. There are 5 membership functions, or equivalently 5 fuzzy sets in the consequent part plane. Then n is equal to 5. In the definition of left order, P is the number of first form fractional membership functions that exist in the consequent part plane. As is seen, in the consequent part plane, there are 2 fuzzy sets labeled by NB and NS, whose fractional membership functions are in the first form. Then P is equal to 2. In the definition of right order, Q is the number of fractional membership functions in the second form that exists in the consequent part plane. As is seen, in the consequent part plane, there are 3 fuzzy sets labeled by Z, PS, and PB, whose fractional membership functions are in the second form. Then Q is equal to 3. Of course, this information also exists in the table. The left and right orders can be determined by substituting the values of n, p, q to the relations and the values of alpha star and beta star drawn from the table. Accordingly, the order of FFIS is the pair 0.2, and 0.4. Let's take a look at another example. In this example, we change the mode of previous FFIS to this mode. In this mode, all the fractional membership functions are in the first form. Okay, let's start to find the left and right orders. The number of fuzzy sets or membership functions in the consequent part plane is equal to 5, the same as before. In the definition of left order, we need to determine the number of fractional membership functions in the first form. There are 5 in the first form, so P is equal to 5. For the right order, Q is the number of fractional membership functions in the second form. There are not any fractional membership functions in the second form. Thus, Q is equal to 0. By this information and using the table, the left order of FFIS is equal to 0.6. But the right order does not exist or is not defined. Therefore, we say that the order of FFIS is 0.6. There is a convention for calculating the order of FFISs, which is useful particularly when we would like to compare or rank FISs. This convention says, consider the same form, first form or second form, for all membership functions whose fractional indices are identical to 1 in all FFISs if you compare or rank them. For example, suppose that there are 3 FFISs in these modes. Since the fuzzy set labeled by Z has not got any arrow, then it means that its fractional index is identical to 1. Thus, it does not matter which form is considered for the membership function of Z. But for calculating the order of FFIS, we need to determine a form, the first or second form, for the membership function of Z. In this situation, the convention is useful. According to the convention, if we choose a form for the membership function of Z in the first FFIS, then the same form for the fuzzy set Z should be chosen in the other FFISs. For example, here in this case, if we choose the second form for the membership function of Z in the first FFIS, then this form should be considered in the other FFISs. Or if we choose the first form for the membership function of Z in one of the FFISs, for example in this FFIS, then this form should be considered in the other FFISs. Now, let's look at an example. There are 3 FFISs in different modes. The tables show the values of fractional indices for each FFIS. The fractional index of the membership function of the fuzzy set labeled Z is identical to 1 because there is no arrow on the top of this fuzzy set. Suppose that we would like to rank or compare these FFISs. Thus, for the calculation of orders, according to the convention, we should choose the same form, first form or second form, for the membership function of Z in all the FFISs. Assume that we have chosen the second form in this FFIS. Then we should consider the second form for the other FFISs. In this setting, the tables are filled in, and the orders can be calculated. We should highlight this point that here, although the subject of ranking FFISs is important, it is out of the scope of this tutorial. Suppose that there is a fractional FIS in this mode. According to the convention, we have chosen the second form for the membership function of Z. A question that arises here is, what does happen for the order of FFIs if the fractional indices approach 1? The answer to this question sheds light on one of the actual results coming from the concept of order. So let's first calculate the order of these FFIs and then gradually increase the fractional indices to approach the integer value 1. This practice reveals another important result. Well, the order of FFIs is 0.2 and 0.5. Now, we have increased the fractional index of PB, PS, NS, and NB, and then obtained the order. Again, we would like to increase the values of the fractional index, but this time we only increase the value of the fractional index of NS from 0.9 to 1. But here, the fractional index of NS is now identical to 1. As we have already explained, there is a convention for the calculation of the order of FFISs. The convention says to consider the same form for all membership functions whose fractional indices are identical to 1 in all FFISs. Remember that we have chosen the second form for the membership function of z because its fractional index had been identical to 1. Thus, according to the convention, we should select the second form for all other membership functions whose fractional index is identical to 1. The fractional index of the membership function of PB is identical to 1, and it has been in the second form, so it follows the convention. In the case of NS, the fractional index of NS is identical to 1 now. However, it is in the first form. Thus, according to the convention, we should change its form to the second form. Therefore, we make these changes. And then the order is calculated in the setting. Let's continue. This time we increase the fractional index of NB from 0.6 to 1. This case is also similar to the previous one. So, by the use of the convention and explanations that have already been provided, the form of the membership function of NB is chosen as a second form. Because there is no membership function in the first form, there is only the right order, which means that the order of FFIs is 0.96. In the last step, by increasing the fractional index of PS to 1, we conclude that the order of FFIs is equal to 1. In other words, the FFIs is from the first order. From the previous sections, we know that a fractional FIS is reduced to its corresponding typical FIS if and only if all the fractional indices are identical to unity. In notations, we shall omit the arrows from the top of fuzzy sets in the consequent part. So we omit the arrows from this FIS that is first order. As you might have guessed now, we can assert that all the typical fuzzy inference systems are in fact first order fuzzy inference systems. There are some questions that should be answered. First, what does happen if the fractional indices approach 1? The answer is the behavior of the FFIs approaches that of its corresponding typical FIS. Moreover, if all fractional indices are identical to 1, then the FFIs is identical to its corresponding typical FIS. In this condition, the fuzzy inference system is from the first order. The second question, how about functional fractional indices? The answer is, if there are functional fractional indices, then the fuzzy inference system is from a variable fractional order. And the last question, where might the concept of order of FISs be used? Briefly speaking, the left and right orders of fractional fuzzy inference systems with the concept of fracture index may be used for ranking and comparing fuzzy inference systems without any need in obtaining the outputs. By the definition of left and right orders, now we know that all typical fuzzy inference systems are from the first order. In addition, the left and right orders pave the way for the introduction of fracture index, which can be used for designing and fine-tuning FFISs. The last concept that is introduced in this section is a fracture index. One of the important concepts which is originated from fractional fuzzy inference systems is what is called the fracture index. The fracture index gives us a relative impression of the marginal behavior of an FFIS with respect to its corresponding typical FIS. By definition, the fracture index of a fractional fuzzy inference system of order R and S, denoted by gamma, is defined as this relation. To illustrate the definition of fracture index, let's look at this example, for which we have already obtained the left and right orders. According to the definition, the fracture index of this FFIS is equal to 0.3. There are some remarks about the fracture index. The fracture index is defined as 1 minus the summation of left and right orders. We know that all the typical fuzzy inference systems are first order FISs. That is, in all typical FISs, the left order is equal to 1 or the right order is equal to 1. Thus, for all typical fuzzy inference systems, gamma is equal to 0. In other words, the fracture index of all typical FISs is equal to 0, which means that there is no fracture in typical FISs. The fracture index of FFISs ranges over the interval 0 and 1. The fracture index makes a sense of the similarity of the behavior of an FFIS with its corresponding typical FIS, particularly for small values of gamma. Specifically, for small values of gamma, as the fracture index approaches 0, the behavior of an FFIS gradually approaches its corresponding first-order FIS. In the next slide, an example is presented for the illustration of these remarks. We have already studied this example, but this time we would like to consider constant fractional indices for both fractional membership functions in the consequent part. To remind, in this example, there are two fuzzy inference systems, the fractional FIS and typical FIS. In both fuzzy inference systems, the falsifier is a singleton falsifier, and the defalsifier is a centroid method. There are only two fuzzy if-then rules in both fuzzy inference systems. The fuzzy sets in both fuzzy inference systems are the same. The inference mechanism in the fractional fuzzy inference system uses the fractional composition rule of inference, in which the base operator is minimum. The inference mechanism in the typical fuzzy inference system is the composition rule of inference, in which the base operator is minimum. Thus, the typical fuzzy inference system is Mamdani's FIS. In the fractional FIS, as you see, the fractional membership function of the fuzzy set B sub 1 is in the first form, or the alpha form. The initial value of the fractional index alpha star sub 1 is 0.3. The fractional membership function of B sub 2 is in the second form, or the beta form. The initial value of fractional index beta star sub 2 is equal to 0.6. To better understand the effect of the variation of fracture index on the behavior of fractional fuzzy inference system, we increase the fractional indices by the step size 0.1, which means that the fracture index decreases. Similar to the previous simulations, here, for each constant value of fractional indices, the input x varies from 0 to 3. The outputs of two fuzzy inference systems are stored in the right-down corner under the title of the history of outputs. The other point that should be expressed is that it can be easily shown that the order of FFIs in this example is alpha star sub 1 over 2 and beta star sub 2 over 2. Thus, the fracture index can be obtained by this relation. So now let's start the simulation. As you see, based on the initial values of fractional indices, the fracture index is equal to 0.55. Then the fractional indices alpha star and beta star are increased by the step size 0.1. Therefore, the fracture index are decreasing. Here it can be seen that for small values of fracture index, as the fracture index approaches 0, the behavior of the fractional FIS gradually approaches its corresponding typical FIS. Thus, the fracture index makes a sense of the similarity of the behavior of an FFIS with its corresponding typical FIS, particularly for small values of gamma. Eventually, when the fracture index is equal to 0, two fuzzy inference systems coincide. On the basis of the concepts of orders and fracture index, we may assert that all typical fuzzy inference systems are fractional fuzzy inference systems of the first order. All typical fuzzy inference systems are fractional fuzzy inference systems whose fracture index is equal to 0. Here, I would like to highlight a similarity between fractional calculus and fractional fuzzy inference systems. Those who are familiar with fractional calculus know that we deal with fractional derivatives and integrals in fractional calculus. Suppose that f of x is a function. The fractional derivative of this function is of order alpha. We know that when the order of the fractional derivative approaches unity, then the fractional derivative of f approaches the first order derivative of the function f. And when the order of the derivative is equal to 1, then we arrive at the first order derivative of f. Similarly, in fuzzy inference systems, the order of fractional fuzzy inference system is a number between 0 and 1. Now we know that when the order of the fractional fuzzy inference systems approaches unity, then the fractional FIS output approaches the first order FIS output. And when the order of fractional FIS is equal to 1, then we arrive at the first order FIS. And in terms of fracture index, when the fracture index of fractional FIS approaches 0, the fractional FIS output approaches the first order FIS output. On the basis of the results of this section, the comparison table can be completed by these two properties. In the next section, we shall investigate some frequent questions arising for readers and provide appropriate answers. But let's have a break time and then continue. In this section, a wide variety of frequent questions regarding the fractional fuzzy inference systems are put on the table, and each of which is investigated with an appropriate answer. Well, here we go. The first question: how is the value or quality determined in FFISs? In FFISs, the truth degree coming from the antecedent part plays the role of the quality or value of information extracted from the consequent part. Here, the FFIS is a single input, single output system. If the system has got more than one input connected with AND operator, then the value or quality for the ICE rule is determined in a usual way by a T-norm defined for the AND operator. For example, here, the minimum operator has been considered as the T-norm. The next question: how is the volume or quantity determined in FFISs? The answer briefly is a fractional index plays the role of volume or quantity in FFISs. Depending on the problem, the fractional indices, functional or constant, need to be designed. It is a part of developing the fuzzy system. There are some suggestions helping us for determining the fractional indices. It is suggested to use the knowledge of experts from the system, trial and error that is related to tuning by the fracture index and some well-known modes of FFISs, using optimization algorithms, using artificial neural networks, or in a general setting, a machine learning algorithms, using ad hoc analytical methods. Next question: how does the volume or quantity emerge in the mathematical relations of FFISs? Where does the volume or quantity emerge in computations? The answer to this question is related to the technical details. Complete explanations have been provided in the following papers. However, a brief explanation is presented here. We use a representation of the typical membership function that is called horizontal membership function. Then, the fractional horizontal membership function is introduced based on which the fractional membership function is obtained. By the use of an operator denoted by H, we obtain the horizontal membership function. H inverse is the operator that operates in a reverse way. It gives us the conventional membership function of the fuzzy set. In notation, the horizontal membership function of the fuzzy set labeled B is also denoted by a subscript H. The horizontal membership function of a fuzzy set is presented in two forms. The first form, or the alpha form, shown on the left hand, the second form, or beta form, shown on the right hand. In this tutorial, we wouldn't like to go through the technical details, so for more details, please refer to the already mentioned papers. So let's continue. By the use of the horizontal membership function, the fractional horizontal membership function is defined. Then, by applying the inverse of the operator H, the fractional membership function is obtained. In fact, this is the process of inferring the fuzzy set B prime by the use of the fractional composition rule of inference in the simple fuzzy inference system f x is A, then y is B. X is A prime. What is y? Y is B prime. As you may remember, when the label of a fuzzy set is only a letter, we could also use a subscript instead of using an arrow. Thus, equivalently, we can write this fuzzy inference system in this form. It should be noted that the base operator in this fractional composition rule of inference is the minimum operator. So the fuzzy set B prime subscript alpha star is obtained by applying the fractional composition rule of inference. In this perspective, a more abstractly comprehensive definition of fractional membership function is presented now. A fractional membership function is defined as the membership function of a fuzzy set resulted from applying the fractional composition rule of inference. This slide shows some details about the relations by which the fractional composition rule of inference propagates the constraints from the premises to the conclusion. Here, this term is the horizontal membership function of B. There are 2 points that should be stressed here. First, it has been supposed that the relation between the value and volume is in the first form in this relation. For the second form, we need to use another relation in which the beta fractional index has been used. That relation is very similar to this one. The second point is that in the original paper, there is a small typo for the presentation of the relation of H inverse. Such a typo does not exist here. So, what you see on this page is the correct relation. In addition, you can find the correct relation in the paper entitled Interval Type 2 Fractional Fuzzy Inference Systems towards an Evolution in Fuzzy Inference Systems. So, you can consider either the relations presented here that you see on the screen, or you may refer to our second paper. Eventually, based on the fractional composition rule of inference, fractional fuzzy inference systems are defined. In this relation, it has been supposed that all the fractional membership functions in the consequent part plane are in the first form. Of course, in most cases, the consequent part plane includes both first form and second form. At a later point, we come back to this relation. But if someone would like to know an abstract definition of a fractional fuzzy inference system, they may refer to this one. By definition, fractional fuzzy inference systems are those in which the propagation rule of constraints is the fractional compositional rule of inference. The next question: what is the relation between FFISs and typical FISs? I think this question has been answered in the preceding sections, but briefly we can say typical fuzzy inference systems are a particular case of fractional fuzzy inference systems, specifically when the fractional indices are identical to 1. The fractional fuzzy inference systems reduce to typical fuzzy inference systems. What are the differences in the configuration of an FFIs with that of a typical FIS? The answer to this question is that the difference in the configuration is related to the inference engine. All the other parts are the same for both the first order and fractional order fuzzy inference systems. Another question: what is the mechanism of inference in FFISs? The inference mechanism in FFISs is based on the fractional composition rule of inference, in which, in a general setting, a relation between the value and the volume of information is made. There are, of course, some more questions. Why should we apply fractional fuzzy inference systems? When should we apply FFISs? Assume that we are given a system that needs to be controlled or modeled, and we would like to use a fuzzy system alone or in combination with other structures. We have obtained some results, but they have not satisfied us. Thus, we apply optimization algorithms, learning algorithms, and other techniques to improve the results. But there is no way to obtain a more satisfactory result. This is why all algorithms, techniques, optimization methods, and so forth have been applied. In other words, informally speaking, we still need a better result. So, what shall we do? One of the answers to this question is increase the type of FIS and use type 2 fuzzy inference systems. This idea may work, but there are some difficulties, among which are using type 2 membership functions in antecedent part and consequent part, computational complexity. Inference block needs to be adapted with the type 2 fuzzy inference systems mechanism, adding type reduction compartments. So, the first answer suggests us increasing the type of fuzzy inference system. The difficulties regarding this answer have been pointed out. The second answer or solution says that increase the range of the order of fuzzy inference system rather than the type, and use the fractional fuzzy inference system. This suggestion advises us to replace only the compositional rule of inference with the fractional compositional rule of inference, a change in the inference block. The computation is based on type 1 fuzzy sets. Eventually, the answer to this question is summarized as, briefly speaking, to obtain more satisfactory results. When you would like to get better results without increasing the type of fuzzy inference systems, you may apply fractional fuzzy inference systems. When there is no way to improve the results, you can apply fractional fuzzy inference systems to pave the way. Note that by the use of fractional fuzzy inference systems, the interpretability is retained while the accuracy increases. The next question. I have used type 2 fuzzy inference systems in a problem. There's no way to improve the results. What shall I do? The answer is, first, you may apply type 1 fractional fuzzy inference systems. If you don't get your desirable results or you insist on using type 2 fuzzy systems, then you are advised to apply IT2 FFISs. The fractional order FISs in terms of type 2 fuzzy sets have been also introduced, which are called interval type 2 fractional fuzzy inference systems, IT2 FFISs for short. For more details, please refer to the paper entitled Interval Type 2 Fractional Fuzzy Inference Systems Towards an Evolution in Fuzzy Inference Systems. In fact, the first order or typical Type 2 fuzzy inference systems have come with the concepts such as lower and upper membership functions based on which footprint of uncertainty is defined, type reduction, and embedded fuzzy sets. This is why interval type 2 fractional fuzzy inference systems presented in 2021 come with more than 10 uniquely new concepts such as interval type 2 fractional membership functions, type 2 fracture index, the concept of switching, the concept of entanglement, the degeneracy concept, cross entanglement, completed cross entanglement, mirrored cross entanglement, completed mirrored entanglement, and the orders of type 2 fuzzy systems. In fact, interval type 2 fractional fuzzy inference systems as the new next generation of fuzzy inference systems can prove themselves as an effective tool in the applications more than all the typical type 2 fuzzy inference systems. In other words, independent of the problem, typical type 2 fuzzy inference systems never yield more satisfactory results than type 2 fractional fuzzy inference systems do. In this perspective, fuzzy inference systems may be categorized as the typical or the first order and fractional order fuzzy inference systems. So, we have the first order type 1 FIS, the first order T2 FIS, the fractional order type 1 FIS that is called type 1 FFIs, the fractional order type 2 FIS that is called T2 FFIs, and so forth. With this understanding that the branch of fractional order fuzzy inference systems are the new generation of fuzzy inference systems. And eventually, it turns out that fractional fuzzy inference systems dominate first order or typical fuzzy inference systems. Next question. Do the results obtained by replacing a typical FIS with its corresponding fractional FIS depend on problems? For example, suppose that I've applied an FFIS instead of a typical FIS in a system control problem, and I've got a better result. Now, suppose that I've applied another FFIS instead of a typical FIS in a classification or clustering problem. Will the FFIS improve the results again? The answer is no, they don't depend on the problem. Yes, it will improve the results. Based on theorems 1 and 2 presented in the original paper, it is demonstrated that independent of the problem, a typical FIS never leads to more satisfactory results than its corresponding FFIs does, provided that a particular set of fractional indices is taken into account. The next question is how to apply. There are two situations. You have designed and already got a system equipped with a fuzzy inference system. You haven't got any fuzzy inference system at your disposal and would like to begin designing an FIS. If so, then construct your own FIS based on any method you would like. Determine the fuzzy if-then rules, the fuzzifier, the fuzzification method, inputs, outputs, and so forth. After you were done, you were in the first situation. Thus, we suppose that a typical fuzzy inference system is available and it works, but you would like to improve the results. 3 steps should be taken. Choosing the operating mode of FFIs, determining the fractional indices, and then applying the fractional composition rule of inference. Actually, this part can be done by the Matlab function FFIs.m. To continue answering the question with more details, let's suppose that you have got a typical fuzzy inference system, such as a Mamdani's FIS, and you would like to use this FIS to control a plant in this feedback control structure. So inputs, outputs, gains, the fuzzification method, and fuzzifier, fuzzy if-then rules are known and determined. So every element of the fuzzy inference system is known, particularly the fuzzy if-then rules. Here, the fuzzy if-then rules have been represented in this tabular form. We know that the difference between a fractional fuzzy inference system and a typical FIS comes from the inference mechanism. Thus, we only need to configure or convert the inference mechanism of this FIS to the inference mechanism of the fractional fuzzy inference system, and all the other parts remain unchanged. We know that the inference mechanism of the fractional fuzzy inference system employs the fractional composition rule of inference, and the fractional composition rule of inference needs to know fractional indices and the operating mode of FFIs. Thus, we need to provide some information about the fractional indices and the operating mode for the FFIs. It should be noted that such information is known for the typical FISs, because the fractional indices in typical FISs are always identical to 1. And we know that the typical FISs always work in the single mode. But for the fractional FIS, we need to provide some information related to the first and second steps of applying FFIs. The fuzzy if-then rules are known in the FIS, and also the consequent part fuzzy sets plane is determined. In this example, the consequent part fuzzy sets plane consists of 5 fuzzy sets. As we said, in the first step, we need to determine the operating mode, and then in the second step, the fractional indices. First, let's choose an operating mode. Suppose that this operating mode is considered for the FFIs, which is actually the aggressive mode. Thus, the surface structure of fuzzy if-then rules is modified according to this mode. For making such a modification, we only need to put an arrow on the top of the fuzzy set according to the consequent part fuzzy sets plane. For example, the fuzzy set labeled PB has got a left arrow, so a left arrow is put on the top of the fuzzy set PB in the table in any place it exists. Similarly, the other fuzzy sets receive their corresponding notations. Therefore, the first step was done. Now, the second step, determining the fractional indices. There are 5 fuzzy sets in the consequent part plane. Then 5 fractional indices should be determined. Since the fuzzy set labeled Z has no arrow, its fractional index is identical to 1. As a result, only 4 fractional indices should be specified. Some suggestions about choosing and determining the fractional indices have already been given in answer to question 2. The last step, applying the fractional composition rule of inference. For applying the composition rule of inference, this relation should be used according to the answer to question 3. As it was explained before, this relation assumes that all the fractional membership functions in the rule base are in the first form. However, in our case, and indeed in most cases, not only the first form, but also the second form of membership functions exists. Thus, if in the ICE rule the consequent part includes a fuzzy set with the first form fractional membership function, then we use the following fractional composition rule of inference. And if in the ICE rule the consequent part includes a fuzzy set with the second form fractional membership function, then we use the following fractional composition rule of inference. Someone may ask, what are the differences between these two relations, first form fractional composition rule of inference and the second form fractional composition rule of inference? Please refer to the answer to question 3 to find out the differences. So because there are two forms, the first and second forms, we shall modify the main relation in this way. So if the membership function in the consequent part of the ICE rule is in the first form, then Z means alpha. And if the membership function is in the second form, then Z means beta. By these explanations, now assume that the section highlighted by green color in the table is the first rule. In this rule, the consequent part includes a fuzzy set labeled NB, negative big, whose fractional membership function is in the first form. Thus, fractional composition rule of inference is in the first form, and Z sub 1 is equal to the fractional index of NB, and the horizontal membership function in the main relation for this rule is equal to the horizontal membership function of NB. Next, assume that this is the second rule, the section highlighted by green color. In this rule, the consequent part again includes the fuzzy set labeled NB, whose fractional membership function is in the first form. Thus, fractional composition rule of inference is in the first form, and Z sub 2 is equal to the fractional index of NB, and the horizontal membership function in the main relation for this rule is also equal to the horizontal membership function of NB. This time, assume that the section highlighted by green color is the 12th rule. In this rule, the consequent part includes a fuzzy set labeled NS, negative small, whose fractional membership function is in the first form. Thus, fractional composition rule of inference is in the first form, and Z sub 12 is equal to the fractional index of NS, and the horizontal membership function in the main relation for this rule is equal to the horizontal membership function of NS. Thus, as a whole, if in the ICE rule the consequent part includes a fuzzy set whose fractional membership function is in the first form, then z sub I is equal to the alpha sub I, and z star sub I is equal to the alpha star sub I, the fractional index of the fuzzy set of the consequent part in the ith rule. And we use the following fractional composition rule of inference. Let's assume that this is the 10th rule, the section highlighted by green color. In this rule, the consequent part includes a fuzzy set labeled PS, positive small, whose fractional membership function is in the second form. Thus, fractional composition rule of inference is in the second form. And z sub 10 is equal to the fractional index of PS. And the horizontal membership function in the main relation for this rule is equal to the horizontal membership function of PS. Similarly, as a whole, if in the ith rule the consequent part includes a fuzzy set whose fractional membership function is in the second form, then z sub I is equal to beta I, and z star sub I is equal to beta star sub I, the fractional index of the fuzzy set of the consequent part in the ith rule. And we use the following fractional composition rule of inference. Although the computation of fractional composition rule of inference is straightforward, you only need to take the first and second step. I mean choosing the operating mode and determining fractional indices. The third step, computations related to the fractional composition rule of inference, can be done by the use of the Matlab function FFISs.m, which will be explained in the next section. So the next questions. These two questions are similar. How to simulate, how to write the programming code. You can simulate fractional fuzzy inference systems by the use of Matlab or any other software like Python. But the function FFISs.m in the Matlab software has been prepared by which you can simulate your projects more conveniently. That how to use the function FFISs.m will be explained in the next section. I have done a project based on Mamdani's fuzzy inference system. So, can I get a better result? How? What shall I do? The answer is yes, you can. You only need to take two steps explained in answer to question 9 and use FFISs.m. You are also advised to pay attention to suggestions given in the answer to question 2. There is an additional suggestion. If the fuzzy sets in the consequent part fuzzy sets plane are symmetrical with respect to the vertical axis, and there is a symmetry in fuzzy if-then rule base, then the propagation of fractional indices should be symmetry and consider constant fractional index equal to unity for the fuzzy sets that are symmetrical with respect to the vertical axis. For example, suppose that there is a fractional FIS whose consequent part fuzzy set's plane is this one. As is seen, the fuzzy set labeled Z is itself symmetrical with respect to the vertical axis. So, according to the suggestion, its fractional index should be identical to 1. In the consequent part fuzzy set's plane, there is symmetry for PB and NB. Thus, according to the suggestion, if the fractional index of PB is the function f sub 1, then the fractional index of NB should also be assigned the function f sub 1. And because there is a symmetry for PS and NS, if the fractional index of PS is the function f sub 2, then the fractional index of NS should also be assigned the function f sub 2. As is seen, now there is a symmetry in the propagation of fractional indices. The reason for such a suggestion is related to the technical details, and thus it's ignored. But one of the results of this suggestion is that, although there are 5 fuzzy sets in the consequent part plane, we only need to deal with 2 fractional indices. In other words, this suggestion leads to a decrease in the number of fractional indices that should be determined. The next question: what are the applications of fractional fuzzy inference systems? The applications of fractional fuzzy inference systems cover a wide variety of subjects such as control systems and automation, image processing, data mining and prediction, combination with other methods, for example fuzzy convolution and neural networks, decision-making and medical diagnosis, fuzzy clustering and classification, multi-objective optimization problem, artificial intelligence systems, learning methods, mobile phones, washing machines, cameras, refrigerators, pressure measure machines, medicine, dishwasher machines, anti-lock brakes in cars, and so forth. And abstractly, in all the areas where typical fuzzy inference systems have been applied since 1975, those FISs can be replaced by FFISs, which leads to more satisfactory results. So a typical FIS is replaced by its corresponding fractional FIS and more satisfactory results are obtained. Someone may ask us this question: what do you mean by more satisfactory results? Let me answer this question with an example in the field of control systems. Suppose that we have employed a typical FIS, for example, Mamdani's FIS, to control a plant. We have also used an optimization algorithm to find the optimal parameters in the control structure and the fuzzy inference system. Thus, now, Mamdani's FIS in this structure has been optimized. Suppose that the blue curve is the trajectory of the system's state, or the system's output, in which the optimal Mamdani's FIS has been used. Informally speaking, this blue curve is the best result that you have obtained. By more satisfactory results, we mean that if the typical fuzzy inference system is replaced by its corresponding fractional FIS, then possibly the result is improved. In fact, I'd like to highlight that what has been obtained as the optimal solutions or optimal results based on the application of typical FISs might not be the optimal results or solutions. Actually, the optimal results are in the other part of fuzzy system outputs space, which can't be discovered by applying typical or the first order fuzzy inference systems. However, fractional fuzzy inference systems as the fractional order fuzzy inference systems enable us to enter a wider space of fuzzy system outputs and eventually discover our desired results. There are also some more subjects in which fractional fuzzy inference systems can prove their applicability and effectiveness. For example, in handoff decision algorithms, educational systems, Internet of Things, fuzzy modeling, psychology, risk assessment, and so forth. Since typical fuzzy inference systems are universal approximators and a special case of fractional FISs, then fractional fuzzy inference systems are also universal approximators. One of the other topics is estimating the error of the approximation of fractional fuzzy inference systems when employed as an approximator, and determining a class of modes and/or fractional indices concerning the estimated error. And the last question, can we apply for a patent through the applications of fractional fuzzy inference systems? The answer is yes, you can. So far, a great number of patents have been registered based on the typical fuzzy inference systems. My impression is that they may be revisited and new patents are registered on the basis of fractional fuzzy inference systems. This is the last section that is about the simulation of fractional fuzzy inference systems in Matlab software. Let's have a break time and then continue. Well, this is the last section of this tutorial, and in this section, a way for the simulation or implementation of fractional fuzzy inference systems in the Matlab environment is explained. The implementation of FFISs in Matlab software may be done through the use of the M file FFIS.m. This Matlab M file function is open source and in the form of a package is available for free on the MathWorks website. The package includes the following 4 files: the help file, the main file, the example file. This is an example about an inverted pendulum system, and the corresponding FIS file that is related to the example. This package is also accessible through the ResearchGate website. The main file that should be used is FFIS.m. This function evaluates fractional fuzzy inference systems. Its role is similar to the eval.fis.m, a function in the Matlab software. So let's first recall eval.fis.m. The data that should be entered into the eval.fis is the crisp input values to the system and the fuzzy inference system that has already been built and loaded by the name of FIS. By the use of this data, eval.fis gives us the defuzzified outputs. For example, suppose that we have built a fuzzy inference system and stored it by the name of tipper. Then, for using eval.fis, we first should load the fuzzy inference system using the command readFIS. Then, the input values to the system should be specified. In this example, the system has got 2 inputs. The eval.fis evaluates the fuzzy inference system and gives us the defuzzified output. To use the eval.fis.m, the following steps should be taken. Design the fuzzy inference system and save it by a name, for example, FIS.fis. Load the FIS, the fuzzy inference system, by the command readFIS. Use the function eval.fis.m to get the output for given inputs. The syntax of the mfile function ffis.m is very similar to that of eval.fis.m. This function converts the typical fuzzy inference system to its corresponding fractional fuzzy inference system, evaluates it for input values in inputs, and returns the resulting output values in the output. The functional indices and the operating mode of fractional FIS take place in the cell array fits. Therefore, the data should be entered into FFIS.m is the inputs, the fuzzy inference system, and the cell array fits by which the operating mode and fractional indices are determined for the system, and FFIS.m gives us the output. To use FFIS.m, the following steps should be taken. Design the fuzzy inference system and save it by a name. Load the FIS by the command read FIS. Determining the fractional indices and the operating mode of fractional fuzzy inference system in the cell array FITs. And finally, use the function FFIS.m to get the output for given inputs. Let's compare two mfile functions, FFIS.m and evalFIS.m. Both functions need a fuzzy inference system built in advance. Then the fuzzy inference system should be loaded by the command read FIS. And then the cell array fits should be filled in. By the cell array fits, FFIS.m is given the operating mode and fractional indices of the fractional fuzzy inference system. This step does not exist in evalFIS.m because typical fuzzy inference systems are single mode and their fractional indices are always identical to unity. The last step is the same for both mfile functions. Therefore, the difference between these mfile functions is related to the cell array fits that should be determined for FFIS.m but does not exist in evalFIS. Now we shall explain how to use FFIS.m step by step. First, we should design a fuzzy inference system and save it. Building a typical fuzzy inference system in Matlab software is an easy task. Building a typical fuzzy inference system. There are two ways to build a typical fuzzy inference system through the fuzzy logic toolbox. First, building fuzzy systems using fuzzy logic designer, and the second, building fuzzy systems at the command line. Figure 1 shows building the fuzzy system by the use of fuzzy logic designer. Here, we shall focus on building a typical fuzzy inference system using the fuzzy logic designer drawn from the fuzzy logic toolbox by using the command by the name of fuzzy in the command window. A default FIS emerges. For building your own fuzzy systems, you should determine the inputs and outputs membership functions. The function FFIS.m in the first version has been prepared such that it only accepts triangular and/or trapezoidal membership functions for the output. In other words, in the first version of FFIS.m, there are only two options can be chosen for the type of membership functions of the output: try-mf and trap-mf. However, there is no restriction on the type of membership functions for the inputs. In addition, the function FFIS.m in the first version works only for the fuzzy systems with single output. Then you should determine the properties of the fuzzy system. In the function FFIS.m, the implication and aggregation have been set to minimum and maximum, but the AND method can be selected as minimum or product operator. The defuzzification operator is also optional. It should be noted that the FFIS.m in the first version works for fuzzy systems in which the variables in the antecedent part connect to each other only by the connector AND. Thus, the antecedent part is not allowed to include OR connector. Next, you should determine the fuzzy if-then rule base. The function FFIS.m supposes that the weight of rule has been set to 1, and as was already stated, only the AND connector is admissible in this version of FFIS.m function. The connectors NOT and OR have not been considered in this version. So the weight has been set to 1. Only the AND connector is admissible in this version. The connectors NOT and OR have not been considered in this version. After building the fuzzy system, we shall export the fuzzy system to the folder in which the function FFIS.m and your main program file exists. It can be done by File, Export to File, and then save it by a name, for example, FIS. The next step is to load fuzzy inference system by the command read FIS in our main program. So the first and second steps already explained are common between eval FIS and FFIS. Those who are familiar with the fuzzy logic toolbox will know how to complete these steps. The next step is the most important step, in which the fractional indices and the operating mode of fractional fuzzy inference system are transferred into the function FFIS.m. The fractional indices and the operating mode of fractional FIS are expressed by the cell array FITs, in which value I determines the fractional index of the i's fractional membership function in the consequent part membership functions plane, and form I is the form of the i's fractional membership function. Value I may be a real number in the interval 0 and 1, or a function of x. For example, it may be a constant such as 0.1, 0.7, 1, 0.68, and so forth. It may be also a function, for example, a sine function, which is written in Matlab File in this form. Form I determines the form of the i's fractional membership function in the consequent part membership functions plane. For the first form, or the alpha form, we should write a between two quotes, or simply the scalar value 0. For the second form, or beta form, we should write b between two quotes, or simply the scalar value 1. Thus, each pair, value I, form I, belongs to a membership function in the consequent part membership functions plane. Let's have an example. Suppose that this is the consequent part fuzzy sets plane of a fractional fuzzy inference system with the fractional indices shown in the table. There are 5 fuzzy sets. Thus, the cell array fits includes 5 pairs of values and forms. Each pair belongs to the membership function of a fuzzy set. NB, NS, Z, PS, and PB. Let's fill in the cell array. For the fuzzy set NB, by looking at the table, the fractional index of its membership function is equal to 0.8. So we should write this value here. Also, it is in the first form, or the alpha form. Then the letter A between two quotes should be written here. We can also write the scalar value 0 instead of the letter A. The FFIs.m also interprets it as the first form. Here, for more clarification, we write the letter A. Similarly, for the fuzzy set labeled ns, its corresponding fractional index value is equal to 0.6, and its membership function is in the first form. So we fill in the cell array by the value 0.6 and the letter A. The fuzzy set labeled Z has got no arrow, and its corresponding fractional index is a constant equal to 1. Then in the place of value, we write the scalar value 1. And for the indication of the form of membership function, we can either write A or B. There is no difference. Please refer to the sections 1 and 2 to remember why there is no difference. Similarly, for the fuzzy set labeled PS, its corresponding fractional index is a constant equal to 0.8, and its membership function is in the second form or beta form. We use the letter B between two quotes to indicate that PS is in the second form. We can also use the scalar value 1 instead of the letter B. But for the illustration here, we consider the letter B. In the same way, we fill in the cell array for the fuzzy set labeled PB. Now, let's consider the case where there are functional fractional indices. For example, suppose that the fractional indices of ns, ps, and pb are functions of mu star in these forms shown in the table. We only need to write these functions in the same way we write such functions in the Matlab script environment, but by replacing mu star with x. So let's do it. For ns, we have this function. First, by replacing mu star with x, we have this function. Then we translate it into the Matlab script language that is this form, and then write it in the place of the value of the fractional index for ns in the cell array between two quotes. Note that if you forget to write it between two quotes, then you will get an error. For the fractional index of PS, we do it similar to the previous one, replacing mu star by x, translating it into Matlab script language, and write it in its corresponding place in the cell array between two quotes. The same thing is also done for PB fractional index. There is an important point that should be remarked here. Remember that we said each pair value and form belongs to a specific fuzzy set in the consequent part plane. The question is, how do we know which pair corresponds to a specific fuzzy set? For example, how do we know that value 1 and form 1 correspond to the fuzzy set NB? Maybe the pair value 5 and form 5 corresponds to the fuzzy set NB. So first we should be aware of the arrangement of fuzzy sets in the consequent part fuzzy sets plane. Then we fill in the cell array. Fortunately, we can easily find out this arrangement. A simple example explains it. Suppose that you have built a fuzzy system whose consequent part fuzzy sets plane is in this form that you watch on the screen. It consists of 5 fuzzy sets. Suppose that you have saved this FIS by the name of FIS. Use the command read FIS to load the fuzzy system. Then, in the command window, run the command fis.outputs.membership functions. The result of this command shows you the arrangement of the fuzzy sets in the consequent part plane, listed by 1, 2, 3, 4, 5. This arrangement from up to down corresponds to the left to right in the cell array fits. In this example, the first pair, value 1, form 1, corresponds to the first fuzzy set, number 1 in the top of the list, that is NB. Similarly, the second pair corresponds to the second fuzzy set, and eventually the last pair on the right hand side of the cell array corresponds to the fuzzy set in the lowest place. Therefore, we could easily find out the arrangement. And now we can fill in the cell array correspondingly. The next remark is that, as explained in the previous sections, in this tutorial, when all the fractional indices are identical to 1, a fractional fuzzy inference system reduces to its corresponding typical FIS. This is also the case here, since the implication is minimum. By setting all the fractional indices to 1, the fractional fuzzy inference system reduces to Mamdani's FIS. Note that determining the form does not important, so X can be either A or B. It doesn't affect the output. This slide shows some examples of filling in the cell array feeds for FFIs in different operating modes and different constant values of fractional indices, and particularly the aggressive mode. There is a question in here that should be answered. The question is, why have you considered two options for determining each form of fractional membership function? I mean, we can write A for indicating that the fractional membership function is in the first form, and we can also write 0 instead of A. The answer is, such an option enables us to find the optimal operating mode of a fractional FIS more conveniently through an algorithm, for example, the genetic algorithm. So the algorithm in its framework can change the scalar values 0 and 1 more conveniently than changing A and B. Finally, the general structure of a program code in Matlab software for applying a fractional fuzzy inference system by using the mfile function FFIS.m may be viewed in this form. In the initialization section, the FIS is loaded by the command read FIS. The cell array fits is filled in, and in the main section, the function FFIS.m is called. For your convenience, this table has been made to show the configuration of FFIS.m. This table can be helpful when you apply the function FFIS.m. Some more advanced versions of the function FFIS.m are released in the future, which will have more optional features, so stay tuned for more updates on the package of FFIS.m. Indeed, anybody who would like to develop this package is welcome. In addition, if someone has got any idea in this regard, they can share with us through the contact links. Finally, the comparison between fractional FISs and typical FISs that has been being completed since the first section in this tutorial is finalized here. I hope you have found this tutorial helpful. For any question, feel free to contact me through the email. Thank you very much for your attention choosing this tutorial and your interest in fractional fuzz inference systems, the new generation of fuzz inference systems.